Hello and welcome back to Communicable, the podcast brought to you by CMI Communications, ESCMID's open access journal covering infectious diseases and clinical microbiology. My name is Angela Huttner. I'm an infectious disease doctor at the Geneva University Hospital in Switzerland and editor-in-chief of CMI Comms. I'm joined again by my co-host, Thomas Tängdén, infectious diseases doctor and clinical associate professor at Uppsala University in Sweden and fellow editor at CMI Comms.
Hi, everyone. Nice to be here.
This is the third installment of our Nightmare series, and the topic today is vancomycin-resistant enterococci. We are delighted to have two guests with us. The first is Professor Kimberly Kline. Kim is one of the world's experts on enterococci, and in 2022, she joined the faculty of the University of Geneva here in Switzerland. Her team works to understand the virulence factors that contribute to colonization, biofilm formation, and infection by Enterococcus faecalis above all, and how these organisms interact with other potential pathogens in human hosts. In full disclosure, I get to teach our medical students with Kim in microbiology seminars every spring, and it is a delight. And I'm so thrilled that Kim is here on the podcast.
Hi, everyone. Thanks for having me.
Our second guest is Professor Lou Rice. Dr. Rice received his medical degree from Columbia University and trained in internal medicine at Bellevue Hospital in New York. Since 2010, he's been chair of the Department of Medicine at Warren Alpert Medical School of Brown University and physician-in-chief of Rhode Island Hospital and the Miriam Hospital in Providence. Dr. Rice is a past editor-in-chief of another great journal, Antimicrobial Agents and Chemotherapy. His research interests include the mechanisms of gene exchange and the molecular epidemiology of resistant enterococcal infection, among other topics. Lou, welcome to Communicable.
Thank you for having me. It's a pleasure.
As our listeners know, we start these episodes with a get-to-know-you question for our guest and also our hosts. Today I'm going to ask, what was your very first job? I'll start. Mine was actually as a guitarist. I used to play a lot of Spanish guitar and would perform at wedding funerals and other events. Most of the times I did this together with my sister who played the flute. How about you, Angela?
So my first job was actually nowhere near as cool. I worked in McDonald's in New York. McDonald's was always hiring, and I have to be honest, I hated it, but I look back and it was extremely informative. I was 16 years old and I learned an awful lot about humanity really fast because it was like a window on the way people deal with each other. Anyway, it was a crash course in humanity, and I think about it a lot even now, many years later. Lou, what was your very first job?
Nothing particularly exciting. My father had a construction company, and one summer, I think before my junior year of high school, I was employed there as a laborer. I hated it. I waited for the coffee breaks and lunch breaks. After about 3 weeks, I quit. It's hard to quit on your father, but I managed to find a job as a gardener. As opposed to the $5.35 I was making working for my father, which was a princely sum back in the 70s, I worked for $2 an hour as a gardener, and I loved it. The lesson I learned from that is that I would never just take a job for money. And since I became an infectious disease doctor, I guess I made good on that.
Okay, thank you. And last but not least, Kim, what was your first job?
Yeah, so I've had a lot of jobs in my life, including things like waitressing and working in food service like Angela. But if I think back to the very first job I had that I got paid in some way, I was actually a very little girl. I had a very short stint as a commercial actress. And by that, I literally mean acting in milk commercials, where I had the task of drinking milk on local TV and acting like I was enjoying it. This was a very short-lived career, but I definitely got paid in the form of chocolate milk.
Very cool. Kim, I did not know this about you. The things we learn. All right, to our nightmare of the day, vancomycin-resistant enterococci. Kim, can you tell us just in general about the characteristics of enterococci, who these bacteria are, what they mean to us humans?
In my opinion, the enterococci are the most fascinating bacteria that exist. And these are members of the healthy microbiota of all of us, really. They exist in the GI tract of humans and animals. One of their coolest characteristics is that they're really hardy organisms. And what I mean by that is they can survive and thrive in a variety of environments. So they're facultatively anaerobic, which means they can actually grow with or without oxygen. It gives them a lot of different niches where they can exist. They can thrive in a wide variety of pHs and salt concentrations, and they're tolerant to bile, and they're intrinsically tolerant to a lot of antibiotics, and they could survive desiccation. So they're just really tough bugs. Historically, there's been two species of Enterococci that are most medically important. This is Enterococcus faecalis and Enterococcus faecium. Who knows what the future holds for Enterococci. As I said, they're members of the normal, healthy gut microbiota, but they also can cause a variety of opportunistic pathogens. As you clinicians well know, probably most commonly they're associated with catheter-associated urinary tract infections, but they also cause bacteremia, endocarditis, a variety of wound infections. These infections can be difficult to treat, especially in the face of antibiotic resistance, which is what we're here today to talk about.
Thank you. That's a nice overview. And now let's talk about the resistance. So Lou, can you give us a background specifically on vancomycin resistance in Enterococci? When and how did they acquire this resistance? What is the prevalence of VRE today? In which countries are they most of a problem right now?
So, as Kim alluded to, Enterococci have intrinsic resistance to a number of different classes of antibiotics that we use frequently. Most commonly cephalosporins, anti-staphylococcal penicillins, aminoglycosides, clindamycin, trimethoprim sulfa. Any Enterococcus you're going to find is going to be resistant to those. We already start out with a limited number of antibiotics. Now, there's never been really any intrinsic or adaptive resistance to vancomycin in Enterococci. It's an acquired thing, and I think that story is really kind of interesting. Vancomycin was introduced into clinical use in 1958. At the time, it was a fairly impure compound. It was dark brown. It earned it the nickname Mississippi mud, and it was fairly toxic. So it wasn't used that much, but with the advent of the 60s and MRSA, vancomycin became used more. It was better purified. And actually, when I was at Bellevue, a hospital, one of my attendings, who was one of the infectious disease attendings, actually said, sometime between 1983 and 1986, vancomycin is the perfect antibiotic. It has been around for 30 years. No resistance has emerged, and therefore no resistance ever will. He spoke a bit too soon. The clinical problem now has to do with two separate lines of infectious disease therapeutic. The first line is the discovery and the clinical use of extended spectrum cephalosporins, particularly cefotaxime, ceftazexime, and ceftriaxone. All three of them were introduced in the early 1980s, and they had fairly widespread use. Enterococci are resistant to cephalosporins, but Enterococcus faecium in particular, the resistant variants of it, highly resistant to these. And one of these, in particular, ceftriaxone, gets very high concentrations in the gastrointestinal tract, achieving concentrations almost 5,000 micrograms per ml in the bile. So we were starting to use a lot of cephalosporins, and so human GI tracts, at least in hospitalized patients, were getting colonized with these highly resistant Enterococci. Separately, something else happened in the late 1978s, and that was the discovery that antibiotic-associated diarrhea was caused by Clostridium difficile. And the recommended treatment for that was first ever oral use of vancomycin. Prior to that, in Europe, gastrointestinal tracts had seen glycopeptides because of the use of an antibiotic called avoparsin as a growth promoter in animals. And that started, I think, in the late 1970s, mid-1970s. All over Europe, animals were getting avoparsin. They became colonized with vancomycin-resistant Enterococci, only it was animal faecium. It wasn't hospital-adapted faecium, and those tended to be penicillin-sensitive, ampicillin-sensitive faeciums. Because it was in the food, it ended up in people. In the United States, avoparsin was never licensed because some fears about a teratogenicity, cancer-causing. And so there was no population that had VRE. And yet, in 1978, it was discovered C. difficile. All of a sudden, people started getting vancomycin. They were getting vancomycin at a time when the faecium population already had shifted over, in my opinion, because of third-generation cephalosporins. If you look at studies back then, they'll show you penicillin-sensitive faecium were prevalent until the mid-'80s, and then by the late '80s, they were all penicillin-resistant faecium. Vancomycin was introduced into that environment. The vancomycin-resistant determinants then got into that population of Enterococci. It was really interesting. In the U.S., there was no community colonization with Enterococci, and yet we had huge problems with infections and colonization in the hospital. In Europe, there was a lot of community colonization with Enterococci, but they had hardly any infections. We have subsequently learned that this is because there are different general clades of Enterococci, and that the most pathogenic of the faecium clades is clonal complex 17 and its various other names. And this was mainly a problem in the U.S. early on, but as will happen, people travel around the world. Everybody uses cephalosporins, and now it's a worldwide problem. Generally, all different variants of clonal complex 17, all highly resistant to both ampicillin and vancomycin. Just a word about the determinants. The two major determinants, Van A and Van B, they're both on transposons, and both can transfer easily between enterococcal strains. In subsequent years, both of these have spread. Van A is more common than Van B, but depending on where you are geographically, you may have a predominance of Van B. They both confer resistance. There are some minor variations in the genetics and the spectrum. Now we know you can sequence a bacterium in a couple of days and you know everything about it. These clonal complex 17 strains have spread around the world. They're the cause of most of the problems. Europe, Western Europe, doesn't have much, according to the most recent European CDC. Now, the most recent data suggests Eastern European countries have a lot of VRE. I'm not sure why that is. If you look at data that they published in 2010, they didn't seem to have a lot. Now they have a lot. Some parts of Africa have a lot. South Africa has reported 76%. Most of these are Enterococcus faecium, although there are some Enterococcus faecalis. And in the U.S., the estimated number of infections per year is 20,000. So you have to separate colonization from infection, which I suspect we'll be talking about later on. But it's really an interesting tale of two different types of Enterococci acquiring the vancomycin resistance genes. But I think it's fair to say that clonal complex 17 has won in terms of hospital-caused infections.
You were saying we had a sort of evolutionary process with third-generation cephalosporins first and then the oral vancomycin usage. Do you think this is reversible? Do you think we can impact the prevalence by shifting to other cephalosporins with lower concentrations in feces? Is it too late?
As with any resistance determinant, if the use of antibiotics tends to promote its prevalence, you can reduce it by reducing those antibiotics. But the horse is out of the barn. These strains are going to be there. Many times these are integrated into the genome. Enterococci just love acquiring DNA. The first faecalis that was fully sequenced is estimated to have 25% of its DNA come from outside sources. I think that they're going to be here, and they will continue to be problems as long as we use antibiotics that tend to promote their colonization.
Thanks for this good context overview. Kim, nowadays, so just looking at today with this different evolution that's been going on, could you say that there are now any intrinsic differences between Enterococci that are wild type and Enterococci that are vancomycin resistant? In other words, are there differences in virulence? Is there a fitness cost to keeping that vancomycin resistance?
So, first of all, I think I would just change the nomenclature a little bit here and say comparing more commensal antibiotic sensitive Enterococci to infection-associated or hospital-associated antibiotic resistant. This is the way I would categorize this rather than wild type. It's a little hard for me to define what that is. And so are there intrinsic differences? Obviously, a primary one is just the acquisition of these van operons that encode vancomycin resistance. So that's a genomic intrinsic difference. On the other hand, in terms of virulence factors, I would say not necessarily. Many of the most well-studied and pretty important virulence factors that we know about, such as the pili that this organism makes, these are encoded in the core genome. These are in all strains, whether they're commensals or antibiotic-resistant strains. And that's true for a number of other well-studied virulence factors. So that doesn't seem to partition with vancomycin resistance per se. But one thing that's really interesting about these antibiotic resistant strains is that they often don't have the resistance to mobile genetic elements that the commensal strains have. And what that means is that they acquire a lot of exogenous foreign genetic material. And this is, as Lou just mentioned, enterococci are really great at acquiring this foreign DNA. These more drug-resistant strains don't have the capacity to reject foreign DNA. They take in a lot. So they have more plasmids and they can incorporate this into their genome. So they have a lot of extra stuff. And this can confer antibiotic resistance, as we're talking about. These can encode additional virulence factors, different additional metabolic capacities. And so this can make them quite different and quite special and potentially more virulent. Is there a fitness cost to vancomycin resistance? This is an interesting question, and I don't think we have enough data to say. There's a couple of interesting studies that have been published looking at comparing commensal strains to vancomycin-resistant strains, and at least in certain situations, commensals can kill certain VRE strains, so they are outcompeted. So this would really suggest that there is a fitness cost to those strains, but whether that's widespread, that was a laboratory study, whether this occurs in a human population, I think we need to learn a little bit more about this before I can say definitively. But Lou, I would love to hear what you have to say about that.
Well, there's two things I have to say. One is that when we normally think about fitness costs, at least when we think about it theoretically, if it's a plasmid, we think it's extra energy to maintain a plasmid. If it's integrated into the genome, it's a little extra DNA. And then the genes have to express themselves. And so those are all extra costs on the organisms. But it's probably less costly when it's integrated into the genome because it's just a little bit more DNA. It's not an independent plasmid. And the thing about these vancomycin resistance determinants is they're inducible, which means they're not even expressed unless there's a threat out there. So the actual metabolic cost is relatively low. And the other thing is, at least when a number of resistance determinants I know of, not necessarily in enterococci, when you can identify a fitness cost with some sort of mutational resistance, and then you continue to passage the organism in an animal without antibiotics, what happens is not that the mutation returns. What happens is you get compensatory mutations, and then the organisms become more fit and retain the resistance. I do think that there is some cost to it because when you really get rid of the antibiotic selective pressure, these organisms tend to go away, or at least go down into small enough numbers that you can't really detect them. It's really hard to prove it.
Lou, who is the patient at risk for becoming colonized with VRE? What are the risk factors?
So in terms of becoming colonized, there's basically two risk factors. One is being around a VRE, basically being in the hospital, and two is getting antibiotics. We can talk about different antibiotics and what might predispose it. You can find studies that will show you many different antibiotics that do it. Early on, we used to favor using metronidazole instead of vancomycin because we thought it wouldn't promote VRE, and then it turned out that metronidazole and virtually all anti-anaerobic drugs promote colonization with VRE. I don't know many antibiotics that haven't been associated, insofar as there might be something to be gained by looking at animal studies. Back in the old days when my lab was doing animal work, we found something interesting. We found that you could colonize mice with VRE by giving them vancomycin orally, giving them a dose of vanco, and all of a sudden, boom, they have lots of VRE in their stool. And then over time, it would go away. The antibiotics most likely to promote persistence of the colonization were antibiotics that had potent activity against anaerobic bacteria. Any of the inhibitor combinations, carbapenems, metronidazole, that was it. And then we thought clinically the cephalosporins seemed to be associated, particularly ceftriaxone. So we looked at the different end. We put relatively few organisms in the upper GI tract while patients were on antibiotics. And in that environment, piperacillin tazobactam actually inhibited colonization. I suspect because it gets such high concentrations in the bile that the few organisms that were coming by were being inhibited, whereas ceftriaxone promoted it like crazy. There's two different things. I think those first few enterococci that you may ingest, are they going to be promoted? Probably if you're on something that has no activity against it, but has very good activity against a lot of other stuff. If you're already colonized, then it's the anti-anaerobic activity. And Curtis Donsky, when he was working in my lab as a fellow, did a study in long-term care patients looking at quantitative VRE and antibiotic associated with it, and found a very, very strong correlation with any antibiotics that have activity against anaerobes. I think it's kind of silly to even think about one antibiotic versus another. Besides, people get multiple antibiotics all the time. Infection is a little different than colonization. And then there's well-defined further things like having had surgery, having devices in your body like catheters, being a hospital patient, especially if you have a weakened immune system, previous infections, neutropenic, dialysis, all those things will predispose you to infection with VRE. But colonization is just a matter of exposure and antibiotics.
So in terms of colonization, you talk about the selective pressure of antibiotics. But how much do you know about the prevalence or colonization rate in the community? Is there a difference between geographical regions and countries? Is that a risk factor going to a country with higher prevalence of VRE in the community? It's well established for ESBL producers and carbapenemase producers, but maybe VRE is not transmitted that much in the community, so it's more of a hospital transmission problem.
That's probably true. I think that's probably true, but I really haven't followed up, and I don't think there are many people looking at the prevalence of VRE in the community. I do know that once they stopped using avoparcin in the European countries, the rates of community colonization dropped substantially within a very short period of time.
Yeah, and the reports that I've seen in the literature are exactly that it's very low in the community, and I've seen that for both the US and Europe.
Kim, so Lou just told us about who is the patient and who will become colonized with vancomycin-resistant enterococci. So the question for you is, who is the patient who will go from being colonized to having an invasive infection with these vancomycin-resistant organisms? How do these enterococci go from being commensals, bystanders, to becoming virulent pathogens? Is it any different for vancomycin-resistant enterococci as opposed to regular enterococci?
I think Lou just touched on the infection aspect and who is more primed to have a more invasive infection. And so these are obviously individuals undergoing antibiotic therapy that allows the enterococci to bloom and grow to these really high numbers. Who's more susceptible? I mean, these are immunocompromised patients or people with other comorbidities such that they can't really fight the infection as well. Individuals on antibiotic suppressive therapy or things like that. On a more micro level, how do they transition from commensal colonizer to pathogen? I mean, there's sort of classic steps to this. They have to colonize first. And then probably a key part of this is they have to grow to pretty high numbers. Again, that's going to happen thanks to antibiotic therapy, clearing out the other members of the microbiome, creating a nice niche for the enterococci to bloom. And that really serves as a nice staging ground for them to breach the barrier in the GI tract. And so there's pretty good data, at least from animal studies, that show once you reach a threshold of enterococci in the GI tract, then they can start to transition across or translocate across the intestinal barrier. This can be promoted by things like inflammation or surgery, injury to the mucosa of different varieties. And once this happens, then obviously they're out of their initial home and they can get to other sites in the body and start to set up these opportunistic infections that they're so well known for. After this, they have to stick in a new site, so they have to adhere to their next destination. So this can be host tissues. This could be things like damaged heart valves, as we see with infective endocarditis, or indwelling medical devices like urinary catheters, for instance. They use a variety of virulence factors that are, in some cases, pretty well studied, like these pili that I just mentioned earlier, to stick to these host cells or abiotic surfaces. These communities that develop of the enterococci, sometimes just by themselves, sometimes with other organisms present. And as they grow to higher densities, they become encased in an extracellular matrix, and this really protects them from a variety of things, mechanical perturbations, antibiotic penetration, immune clearance. And so this ability to form biofilms is really, I think, one of their hallmarks in terms of pathogenesis, and it can make these infections harder to treat. At that point, once they've established these biofilms and are establishing infection, Another thing the enterococci need to do is evade the host immune system, and so the biofilm structure certainly helps them with that. What we've been learning in our lab, and others have been studying this as well, is with faecalis, they have a number of mechanisms to evade the immune system. They can resist neutrophil killing, they can survive within different immune cells, and actually we've recently found that they can replicate in a variety of mammalian cells, including immune cells. So not only do they avoid clearance by these immune cells, set up shop in them and use this to replicate, they're pretty good at evading the host response, at least at some level. And so I'd say these are the classic steps of pathogenesis. They have to colonize, they disrupt barriers, they have to adhere to new infection sites, they form biofilms, and they have to evade clearance by the immune response. Angela, your last question was, are there any differences between commensals and VRE in terms of this pathogenesis? And I would say probably not. I mean, I think the VREs probably just have an initial advantage because in the face of antibiotic treatment of vancomycin, they can just keep growing and grow to higher numbers and set up this overgrowth more readily at the outset.
Yeah, thanks. Interesting.
Thank you. To me, it sounds like a super bug. So Lou, for the less specialized in our audience, can you tell us how VRE is diagnosed? Are there any new rapid diagnostic tests in the horizon that you think will have a clinical impact?
Well, it depends. Colonization versus an infection. An infection is just the way we would typically diagnose any infection. If it's a blood infection, you draw blood. If it's a wound infection, you take a sample of the wound. Abscess, you drain the abscess, and then you sample that. You grow it, what you can grow in the laboratory, and then you do susceptibility tests. That's pretty standard. Enterococci are easy to grow, easy to identify. Some of the susceptibility tests, most of them are very reliable. In well-resourced countries, it's pretty automated by tech, microscan, sorts of things. The only issue with that is that the standard broth for growing all susceptibility testing is Mueller-Hinton broth, which doesn't really support enterococcal growth well. Brain-heart infusion is much better for Todd Hewitt. In less resourced countries, you might find more disc susceptibility testing or strip susceptibility testing, which have some reproducibility issues with enterococci. There are assays out there for detecting stool colonization that look for Van A and Van B. The Van A tends to be more sensitive and specific. I think the Van B is not so much. And I think part of the problem is that there are some anaerobic bacteria that are probably the origin of the Van B determinant that might be there but aren't pathogenic and might fool you. Not sure about that. But depending on where you are and what the issue is, then you can have rapid tests diagnose it. But in general, most people are doing it by culture.
And the rapid tests you mentioned are for screening of fecal samples mainly, or?
Yes, it's generally used for screening fecal samples.
Yeah. But then you would miss some other Van types. You mentioned two of them, but there are also others, right? Or you would rather overestimate the carriage rate because you have these falsely positive results.
So there wouldn't be too many false positives with the Van Bs. Yeah, there are a number of others. There's something called Van C, and that is intrinsic to several species of Enterococci, Galenarium, Caselli flavus, I can't remember the third. They cause very rare human infections, and if you identify them as a species, then you know. The difference is that the precursor that is altered in Van A and Van B is putting a lactate instead of an alanine on the end of the precursor, whereas the Van Cs have a serine instead of a lactate. Same general idea, but I don't think there's any reason to be screening for the others. Certainly not molecularly. They're actually quite rare. And if you have an outbreak, then you can just do that specifically.
Louis, I have another question for you. So what do you do in terms of infection control once you've made the diagnosis? As you probably are well aware, there's this big debate going on regarding gowns and gloves for MRSA right now. Are there the same questions for VRE? And based on that, what would you recommend for low resource settings?
I can tell you at our hospital, we just have standard precautions for people with VRE, and we don't screen. Now, my hospital doesn't have a large transplant unit. We don't have a bone marrow transplant unit. We don't do liver transplants. But these are the patients that, if they become colonized with VRE, are very hard to treat and they're the ones who are going to die from it. The infection control people here have made the decision, and I think it's a reasonable one, that we're just going to use standard precautions, which involves gloves if you're going to be coming in contact with any kind of fluids, gowns if necessary, but not strict contact precautions, which we actually have for MRSA. So we're on both sides of the fence in that one. MRSA and VRE are different in that MRSA can certainly colonize the stool, but VRE, stool just gets everywhere. It's impossible to keep it from going all over the place. And I agree with, in a hospital that doesn't have huge problems with immunocompromised patients who are going to really suffer from VRE infection, it's reasonable to save your resources for where they're necessary. But in a bone marrow transplant unit, I think it's reasonable not only to screen, but to do the full contact precautions for anybody that has it. Because, like I said, there's becoming colonized is two things. You got to get exposed, and you got to get antibiotics. There's no bone marrow transplant unit in the world that I know of that everybody doesn't get a lot of antibiotics. So you're not going to change that. And so the only thing you have a possibility of affecting is the transfer of the organisms. And in that high-risk environment, I think it's probably worth the effort to do it.
Thank you. So Kim, to follow on that, do you think person-to-person transmission is the main driver of VRE, or is it mainly the selective pressure of antibiotics?
Yeah, it seems to me that these are probably interrelated things. As Lou just said, these organisms are really good at sticking around, and so this really facilitates person-to-person transmission via inanimate objects or directly. And this certainly then contributes to the spread of VRE, and obviously in hospital or long-term care facilities, this is a bigger issue, and that they can stick around and continue to spread. What is the contribution of the selective pressure of antibiotic use? That's a big driver, of course. Antibiotic treatment will select for those even rare resistant organisms and allow them to grow to much higher numbers. It can also promote this growth to much higher numbers in the GI tract, and then this can, of course, lead to greater likelihood of spread, either in terms of opportunistic infections or throughout the hospital settings. And this can feed back to increased transmission within the healthcare setting. Probably the antibiotic pressure is going to be the primary importance, but person to person or person to object to person spread certainly facilitates the spread of this organism.
Yeah, so what can you say about the growth on objects in the hospital environment? For how long can a VRE grow?
I'm not sure I would say grow, but certainly persist.
Survive.
Survive for a really long time. I mean, these bugs are really tough. I've heard some local stories of, big problems, them just sticking around in drains and crevices in places where they shouldn't be, despite pretty strong infection control strategies. And so they're good. They can dry out. They can sit around for days. You have to really work hard to kill them, even in the laboratory, I would say.
Louis, moving to more, really invasive disease, you recently wrote a very concise executive summary for CID on persistent enterococcal bacteremia. Can you tell us in broad strokes what are the diagnostic considerations for bacteremia and what are the therapeutic considerations?
It was persistent enterococcal bacteremia. Enterococcal bacteremia is just positive blood culture. Persistent is, when you look through the literature, there's a dozen different definitions. So comparing studies is difficult. Is it persistently positive after the first positive culture, or is it persistently positive after antibiotics have been added that are clinically or in vitro effective? How many days? I think that the important point, without getting into definitions and how do you diagnose that, there's just a couple of things that you have to do. One is, if there's any chance that you can improve the patient's immune system or that it will get better, such as someone who's neutropenic and is going to recover their white cells after a period of time, that will give you some hope. Otherwise, can you reduce the inoculum of the infection? Everything in antibiotics is just a numbers game. Can you get the antibiotic there in big enough numbers to inhibit the number of organisms there? If you can decrease the number of organisms, then you're better off. If you can increase the delivery of the antibiotic, you're better off. If the infection is an abscess, drain it. If the infection is osteomyelitis, debride it. If it's in the urinary tract, it's probably a low inoculum infection, so you don't have to worry about it. If it's on a heart valve, man, you're in tough shape. If it's on a prosthetic device, you're in tough shape. Because, as Kim said, these are very good at persisting even in the presence of antibiotics. Their tolerance to beta-lactams is really clinically important. Endocarditis cure rates when people just used penicillin were about 40%. When it was discovered many decades ago that penicillin plus aminoglycosides had a synergistic killing effect on the Enterococcus, this is mostly faecalis, cure rates went up to 80 to 90%. So that's a really clinically significant importance for the tolerance. Frankly, it's the only tolerance of any bacteria I know of that is clinically important and reversible by use of combination antibiotics. I would say try to identify the source, get rid of as much of it as you can, and then use antibiotics that are active in vitro. I know that's very simple, but that's really what it comes down to.
Sounds reasonable. So getting more specific, Lou, which antibiotics do you recommend for VRE infections, depending on the site of infection?
If I could divert for just 1 second. When VRE first came around, there was a lot of attention paid to it. And the reason for that was vancomycin was the only drug we had to treat Staph aureus that was resistant to methicillin. And we were all scared to death that this was going to get into staph because they'd shared beta-lactamase genes, they'd shared erythromycin genes and transposons, they'd shared gentamicin genes, or at least found them from the same source. So there are plenty of examples of genes that became prevalent in both species. I have no idea why staph don't like vancomycin resistance. It's weird, any more than I know why beta-lactamase has only been so rare in Enterococcus. But it's an interesting thing. And fortunately now, I think, I hate to sound like my old attending, but if vancomycin resistance hasn't gotten into staph after 3 decades, maybe it won't. I don't know. I'm not going to say anything definitive. So what are the drugs we have? Fortunately, and most of these drugs were really developed for staph because we were worried about vancomycin-resistant staph. The 2 mainstays are daptomycin and linezolid. Daptomycin is a lipopeptide. It's effective. It can be bactericidal in some cases. Resistance can emerge to it. Linezolid is oxazolinone. It is strictly bacteriostatic. It's a protein synthesis inhibitor. And those are the 2 that we use. That you can use some combinations of them. Some people use daptomycin with beta-lactam like ceftaroline. I don't know that there's a lot of great clinical data to support that. Some in vitro data. But those are our 2 main go-to drugs. There are some newer glycopeptide-like drugs like iridovancin that people use sometimes, but I really haven't used that very much.
So again, for Lewis, what do we really know about necessary durations for deep-seated VRE infections like osteomyelitis, for example? Do we really need to treat so long? What is your real-life experience with linezolid long-term? Our patients want oral options. What do you recommend as a safety schema for patients who need to take linezolid for more than a few days? Because we struggle with this here.
Yeah. So the 2 major issues with linezolid are its impact on platelets and the potential for a serotonin syndrome in people who are on selective serotonin reuptake inhibitors. And the platelet issue with linezolid is real, and it is related pretty strictly to how long you've been on it. If you're on it less than 2 weeks, it's much less. It's thrombocytopenia, it's lower platelets. If you're on for more than 2 weeks, then it goes up. And the numbers, there's somewhere between 15 and 20% of people will have thrombocytopenia. So if someone needs to be on linezolid, you got to watch their platelets. There's really no way around it. And it is reversible once you stop it. So it is hard to give people long courses of linezolid. The SSRI business, honestly, at least the data that I've looked at, larger studies, seems to be pretty rare, like less than 1%, considerably less than 1%, maybe 0.5%. I think the current recommendation now is that if you don't think the patient needs any SSRI acutely, then stop it while they're on linezolid. If you feel that there would be bad things that will happen if you take them off, then just keep an eye on it. But that, it's less than 1% of people. In one study, it was less than 1% in elderly patients who were on SSRIs. So I think that was a little bit more overblown than it needed to be. But the platelets are real, which is why people tend to look more at daptomycin if they can. But then again, linezolid has the beauty of being 100% bioavailable orally. It is an attractive alternative.
And so for you, this SSRI issue, it's a relative contraindication. It's not an absolute contraindication because of that 1% or less.
Yeah.
And just to drill down a little on the thrombocytopenia, how often do you check those platelets? Do you do it every week, every 2 weeks, when you know your patient needs to be on linezolid for a good 4-week course or 6-week course?
Every 3 or 4 days. I get nervous when people's platelets go down. Maybe you shouldn't listen to me on this because I don't follow patients outpatient. Talk to my ID colleagues. I treat people in the hospital, and we discuss these things. And because I'm a hospital doctor and we can test anytime we want, I tend to think of it more. But once the platelets start dropping, they can drop, and I'd rather stop it. I think you should check it at some reasonable level. I would ask an expert, which is not me, on that.
It really depends on the individual here, on the individual clinician. We check here, I would say, not more than once a week, honestly. But we don't like to give it for very long because it's
That's real. There's no question about it.
Yeah.
It's anything that occurs in 15 to 20% of patients has the potential to cause you to bleed in your brain. You got to pay attention, so you'd rather just keep the patient off of it.
So do you normally check drug concentrations, the TDM for linezolid?
No, but
No.
There have been people who have recommended it because there, as it turns out, a risk factor in some studies for the platelet drop is renal insufficiency. And only 30% of linezolid is excreted unchanged in the kidney. The rest is metabolized. And between linezolid and the metabolites, it may be that those are the things that cause the platelets to go down. And when they've looked at linezolid concentrations in patients, mostly in ICUs, because that's a lot of patients who are getting the linezolid, some people have very high levels and some people have very low levels, and it's hard to predict. In the studies that have been done, they haven't shown that the high or low levels have a correlation with the outcome, which probably has to do with the fact that anyone who's getting linezolid in an ICU has a lot of problems. Attributing outcome to any one thing is devilishly difficult. They probably have 10 other problems that would kill them.
That's true. Yeah. So again, this is a real problem with linezolid. Do you know if there are any other new oral antibiotics in the pipeline for VRE?
Yeah, no. Their urinary tract infections can be treated, it's not really new, but treated with vancomycin. But no, and I'm not as hooked into the pharmaceutical companies as I have been in the past, but I asked my successor as the editor-in-chief of AAC, Cesar Arias, who is very tied into all things Enterococci, and I said, are there any new agents out there you know of, anything investigational? And he talked about one microbiome type of product that might be used, but that's not treatment. That might be for colonization. So no, there's no white horse coming over the horizon. You know, one of the problems is that it's really, really hard. And pharmaceutical companies have basically given up on getting an indication for enterococci, for VRE, because it's so hard to get the number of patients you need into these studies. You want a clinical study, you want patients to be relatively clean, you want them to have one problem, you want the problem to be accessible, and that's exactly not the patients who get VRE, bacteremia. I think linezolid is probably the only drug. Sinercid did before, but that's not really around much anymore. And linezolid does have an indication for VRE, but daptomycin doesn't. They decided that it was just too expensive. It would be too expensive to get an indication. I guess the best we can hope for is that some new anti-staphylococcal drug will be active against VRE as well, because people will develop drugs for staph.
How about decolonization strategies for VRE? You mentioned the microbiome, and are there other alternative strategies to get rid of carriage?
Yeah, people have tried to decolonize for VRE since the beginning. People tried it with chloramphenicol, and the problem is you got a huge inoculum of bugs in there, and you got bugs that don't want to die, and you have bugs that are very good at acquiring resistance. And so none of them have really worked well. Of late, I've looked at a couple of protocols that address one of these problems by combining either antibiotics or not antibiotics with a polyethylene glycol administration into the gastrointestinal tract. So you guys look very young. Maybe you haven't had your colonoscopy yet. But I can vouch for the fact that polyethylene glycol treatment cleans you out really well. And then they follow that up. They'll follow that up with lactobacillus to try to colonize, and maybe some antibiotics. On the theory that the inoculum is way down, maybe you're really actually going to be able to get rid of it. One study, it cleared about 57% of people, but so did placebo. And there was an uncontrolled study that was similar, that 62%, but they didn't have a control. The other thing on the horizon, which may have some hope, is bacteriophage studies, or bacteriophage treatment. And there is a product, there's a company, it's called Intralytics, and they have FDA approval for a clinical trial testing a cocktail of bacteriophages specifically for decolonization with VRE. So it may work. There's a case report in MBio just March this year. They talked of a case where a patient had recurrent VRE bacteremia. She was immunocompromised, recurrent. Basically, they couldn't get rid of it, even with whatever antibiotics they tried. They added a bacteriophage that was active against it, both intravenously and in the gut. And that seemed to clear it out pretty well until it recurred some months later. And then they added a second bacteriophage to it. At that point, it worked for a bit, and then it didn't work. And then they identified some serum antibodies against the bacteriophage, which is generally one of the limitations of giving bacteriophages. But the limitation in the gut is more that bugs tend to become resistant, although none of the bugs they identified became resistant to the bacteriophage, so they thought that the failure was due to the humoral immunity against the bacteriophage. So, I mean, it's something worth exploring, but there's nothing that's really on the horizon that's going to be clinically available too soon.
So how about vaccines or a simple fecal transplant?
A fecal microbiological transplant has been great for C. diff. There may be studies out there, but I'm not really aware of ones that have looked specifically for VRE. I'll tell you what my basic philosophy is, that the real problem of trying to get rid of VRE is that the patients who get it tend to be very sick, and so they're going to get more antibiotics. They're just going to. In that study I referred to that Kurdistansky did, it was published in the New England Journal back 25 years ago, the vast majority of patients in that study got subsequent antibiotics. Everybody got subsequent antibiotics because they're old, they're sick, they have immune compromise. And anytime you recolonize with lactobacillus and then you blast them with antibiotics, what do you think is going to happen to that lactobacillus? See you later.
That sort of implies that you don't really get rid of all the VRE, you're just suppressing them, they're still around.
Yeah, I think that Kim described it very well. They have lots of tools to persist in the human GI tract. There was an interesting article in Cell by Mike Gilmore and his group where they traced the differentiation of Enterococci way back to when we crawled out of the ocean and became terrestrial. They traced all the various virulence things that they have that would really suit an organism that was going to be a terrestrial organism as opposed to an ocean organism. I may be terribly misstating that. But
yeah, I think that's my take home as well. They've co-evolved exceedingly well to survive and thrive in our GI tracts.
So, coming back to you, Kim, we haven't talked much on the species level. Beyond antibiotic resistance, are there differences in behavior between E. faecalis and E. faecium, between these species and some of the other species that we are starting to see more and more in the clinic?
Yeah, there are differences. And I think you said besides antibiotic resistance, but I think that's actually important to highlight here because there are these differences. And Lou mentioned this, that VREs are most often faecium, at least those that you're dealing with clinically. So faecium is generally thought to be more antibiotic resistant than faecalis. And so that makes it potentially more of a problem clinically and more difficult to treat. And it's not just VRE, but other antibiotics as well. Faecalis, I think, generally is more susceptible to antibiotics, including vancomycin, and so maybe less of a clinical problem in that respect. But of course, if it becomes VRE, then it's as big of a problem as we've been discussing. I think we can also think about virulence factors and the difference between the species on that level. Faecalis certainly has more well-described virulence factors compared to faecium. I think part of this is because it's more thoroughly studied. There's been more people working on it over the years. And so some of these include things like secreted cytolysins, secreted proteases, surface-associated adhesins, things like this that contribute to its ability to cause this wide variety of infections that I mentioned earlier: endocarditis, urinary tract infections, wound infections. So it's pretty good at pathogenesis in general. And as I mentioned as well, faecalis is really good at forming biofilms. And so this is an important trait of it. Generally, I think faecium is considered a little less virulent, at least in terms of classical virulence factors. But of course, it's evolved in these hospital environments to be really adept at surviving in harsh conditions, particularly in the face of antibiotics. And faecium is also really good at biofilm formation and resisting desiccation and disinfectants. And so these are some of its virulence factors. But the classical virulence factors are less well described in faecium. And this is a place I think we need a lot more study, just because I think the efforts haven't been matched to faecalis here. And then we can also think of species-level differences in terms of epidemiology. Faecalis is still the most common or frequent cause of enterococcal infections, particularly community-acquired infections like UTIs and endocarditis. And these infections often are associated with more invasive procedures, not the community-associated ones, obviously, but things like catheterization or surgical interventions. That said, although the numbers are lower, faecium is more dominant in these hospital settings where antibiotic pressure is high. The epidemiology and where we're seeing these infections is a bit different for these species. When we think about other enterococcal species, Gallinarum, Cassiflavus, Raffinosus, are the ones that come up in the literature most often as secondary vectors in terms of the enterococci. These are pretty interesting. We don't know a lot about them. There's not so much research being done on these compared to faecalis and faecium. As Lou mentioned, Gallinarum and Cassiflavus at least have this vancomycin gene, so this provides intrinsic resistance to low-level vancomycin. But these infections are generally not as common, at least so far. They have some virulence features that the other more frequent enterococci, faecalis and faecium, don't have. So Cassiflavus has this yellow pigment, and certainly in other organisms, pigments have been associated with virulence. And as far as I know, this hasn't been examined for Cassiflavus, but I wouldn't be surprised if this is important for its virulence. And these are also modal enterococci, so they have flagella, and this is not true for faecalis and faecium. And so I think this is fascinating to understand why it is that they've held on to their flagella and the others either never acquired it or lost it along the way. We have a lot to learn about the virulence of these less common species, and especially, as you say, Angela, they're becoming more common in hospital settings, and I think that should be a strong motivation for us basic researchers to take this on and try to understand them a little bit better.
Yeah, it's scary that some of them have flagella, but we don't want that. It's not good.
Speaking about that, the need for more knowledge. So here's a question for both of you. If you were granted $10 million for VRE research, how would you use it?
I would fund Kim's lab.
I'll take it.
I'm an antibiotic person. I'd love to see more different, better targets for inhibiting the organisms. We need more antibiotics.
Yeah.
And Kim, do you agree?
I definitely agree with that. You know, the enterococcal research community is so awesome. There's people like Lou, who I don't get to see nearly as much as I would like, but every time I get together with the community, I'm so inspired. It's such an open, friendly, and supportive community of researchers. New ideas just bubble up. And so in my dream scenario, I might need more than $10 million, but I would try to set up an enterococcal research center, and I would bring together the best, brightest, youngest people that have their fingers in the newest technology with the newest ideas. And I would place myself somewhere in the periphery so I can play along with them. But I think that would be the coolest way to spend a lot of money. And advanced enterococcal research is including, as Lou said, things like understanding alternative targets, understanding this bug better so we can figure out better, more efficient ways to treat these infections.
That sounds good. So let's hope you get the grant.
Oh, I love that, Kim. Federating researchers. It's too cool. As we come to a close, Kim and Louis, again, question for both of you. What are the key messages you want to leave our audience with?
Be careful with your antibiotics. I was looking up these data. Europe is pretty good. About 30% of people who get admitted to hospitals in Europe get antibiotics. The US and China, it's about 50%. Some parts of the world, 70 to 80%. We have to be more careful. Just too many people are getting these drugs who really don't need them.
Thank you very much. Yeah, it's a message we just can't say enough. Kim, how about you?
I would say clinicians, talk to your basic researchers, and basic scientists, talk to your clinicians, because this happens to some degree, but I think probably not enough. And some of our best ideas and suggestions come from clinicians. You guys are seeing what's happening on the ground, and this really can inform our research. But I think it goes the other way as well. In the lab, we stumble across really funny, interesting things, some of which are probably just curiosities and they're irrelevant to clinical practice. But, every once in a while, some of these curiosities strike a chord with the clinician and they say, oh, wait a second, this sounds familiar. And those conversations can be really productive and idea generating. And I would say for both ways, I think more interaction that way is never a bad thing.
So Kim, you're saying we have to hang out a lot more.
Absolutely.
I completely agree. Thank you so much to our guests, Kimberly Kline here in Geneva, Switzerland, and Louis Rice in Providence, Rhode Island. And thank you for listening to Communicable, the CMI Comms podcast. This episode was hosted by Thomas Tängdén and Angela Huttner, editors at CMI Comms, ESCMID's open access journal. It was edited by Dr. Kathryn Hostettler and peer-reviewed by Dr. Nunzia Esposito of the University Federico II of Naples, Italy. Theme music was composed and conducted by Joseph McDade. This episode will be citable with a written summary referenced by a DOI in the next 8 weeks, and any literature we've discussed today can be found in the show notes. You can subscribe to Communicable on Spotify, Apple, wherever you get your podcasts, or you can find it on ESCMID's website for the CMI Comms Journal. Thanks for listening and helping CMI Comms and ESCMID move the conversation in ID and clinical microbiology further along.